Swayam Prabha. Digital India. Educated India.
So till now we have seen how to obtain the intersecting contours and how to create the polygons with the intersecting lines by appropriately shorting them. Now it may happen that while doing the slicing for a particular object, the multiple contours may obtain. Some contours may be corresponding to the exterior and some contours corresponding to the interior. Such an example is given here in this diagram. This is the data of the contours which we have obtained after slicing at a particular height. It can be seen that there are several contours here. Now, the objective here is to identify which contour is corresponding to the exterior and which contour is corresponding to the interior. Meaning that if I am getting this type of contours, I know that the material will be here. And there will be no material here. Again, there will be some material here. And there will be no material here. Again, there will be material here and there will be no material here. In a similar fashion, the material will be here and the material will be here. Now, how can we identify these contours automatically? For example, the contour number 1, which is this particular contour, is the exterior contour of the object, while the second contour is the interior contour of the object. It becomes very important to appropriately organize these contours in such a way that the algorithms can easily read these contours and give us the appropriate results. For that, let us create a relationship matrix in such a way that if there are contour I and contour j, an appropriate value will be assigned to that cell. So for example, a matrix has been created here. It is a 9 by 9 matrix. This dimension is coming because there are 9 contours involved and we are trying to stabilize a relationship between the different contours. That is why 9 by 9 matrix, and hence there are total 81 cells here. Now our objective is to fill these cells appropriately in such a way that we can easily identify the contours corresponding to the exterior and contours corresponding to the interior. For that, we have given a rule here. The cell ij of the matrix R will be equals to 1 if the contour I contains contour j. Also, the cell ij of relationship matrix R will be minus 1 if the contour I is contained in contour j. Also, the relationship matrix ith and jth cell will be 0 if the two contours are separated. And if I is equals to j, that means we are trying to establish the relationship between the same contour, then its value will be plus 2. It is also very easy to identify whether the contour is inside the another contour or not. Why? Because when we do slicing, it is obvious that we always get non-intersecting contours. Hence, we can check any point on the contour whether it is inside or outside of a particular contour. If it is inside, then entire contour will be inside, and if it is outside, then the entire contour will be outside. In other words, as there are no intersecting contours, an in polygon test can be used to identify the father-son contours. There are several algorithms for in polygon test, such as ray casting algorithm and winding number algorithm. Also, if you are using the platform like Python or MATLAB, the in polygon test libraries are already available. You can directly use to check whether the point is inside the contour or not. Now let us fill the relationship matrix. For this particular cell, I is 1, j is 1. That means I is equals to j, hence we have to write 2 here. Then let us consider the next cell. I is equals to 1 and j is equals to 2. And the ith contour is containing the jth contour. You can even see here also. How you will do in your programming language? You will just consider any point on the second contour and test it whether it is inside the first contour or outside. If it is inside, that means the entire contour will be inside the contour 1. By seeing here also, we can clearly say that the contour 2 is inside contour 1. Hence, we need to write plus 1 here. Again, contour number 3 is also inside contour number 1. Hence, we will write 1 here again. Contour 4 is also inside contour 1. Contour 5 is also inside contour 1. Contour 6 is also inside contour 1. And contour 7 is also inside contour 1. Now, let us test for the contour 8 and 9. Contour 8 and 9 are outside the contour 1. That means they are the separated contours. Hence, we have to apply this particular case and hence we need to write 0 here. Now, let us move to the next row, that is corresponding to the second contour. Second contour is contained inside the first contour. That means I will write minus 1 here as per the definition given here. If the ith contour is contained in jth contour, I need to write minus 1. And it can be seen second contour is inside contour number 1, hence minus 1. Then for 2, 2, I need to write 2 only. Then the second contour, it is containing the third contour. That means I will write 1 here. Similarly, second contour is containing fourth contour, fifth contour, sixth contour as well as seventh contour. While the 8th and 9th contour are outside. Let us consider the next row now. Contour number 3 is inside contour number 1, hence minus 1 here. Contour number 3 is also inside contour number 2, hence minus 1 here. And for 3, 3, I equals to j, I need to write 2. Then contour number 3 is containing contour number 4, hence 1 here. Also, contour number 3 is containing 5 and 6th contour. But we can observe that the contour number 3 and contour number 7 are separated, hence a 0 will be written here. Similarly, contour number 3 and 8 are separated, hence 0, 0 here as well. Now let us consider the contour 4. Contour 4 is completely inside contour 1, it is inside contour 2, it is inside contour 3 and it is having same relation for 4, 4 and it is separated from 5, hence 0 here, separated from 6 also, hence 0 here, separated from 7 and separated from 8 and 9 as well. Now let us consider the fifth contour. Fifth contour is inside 1, fifth contour is inside 2, fifth contour is inside 3. It is separated from 4 and for 5, 5 I need to write 2 and it is containing sixth contour, hence 1 here and 0 for 7th, 8th and 9th. Now let us consider the sixth contour. It is inside 1, it is inside 2, it is inside 3, it is inside 4, it is separated from 4, hence 0, it is inside 5, hence minus 1 and for 6, 6, 2 and then it is separated from 7, 8 and 9. Then let us consider 7. 7 is inside 1, 7 is inside 2 and it is separated from 3, 4, 5, 6. and 2 here, and it is also separated from 8 and 9. Seventh contour doesn't contain anything. Then the 8th contour, it is separated from 1, it is separated from 0, 3, 4, 5, 6, 7, and also it is containing 9, hence 1 here. Now let us consider the 9th contour. 9th contour is also similar, it doesn't contain or containing in 1, 2, 3, 4, 5, 6 or 7, but it is inside 8, and I am going to write 2 here corresponding to 9, 9. So like this we can define a relationship matrix that shows the father and son relationship between the contours. This is one way of defining such data structure. There could be some other ways also. Now let us see how we can utilize this developed data structure to extract the information related to the exterior and interior contours. Now let us look at this matrix. Now let us try to extract the information from this relationship matrix. There are two possibilities. One is for a contour I, if J we consider for all the columns, any cell is having value not equals to -1, then it is a separate exterior contour. For example, let us look at this contour number 1. It doesn't have anywhere in any cell for different values of J, there is nowhere -1, hence it is a separated exterior contour. Also we can see contour number 8, it is also not having any cell containing -1, therefore contour number 8 is also separated exterior contour. Now let us consider the another case where there will be some cells with Rij equals to -1. Then it means it is a contour contained by jth contour, and if the number of times -1 is occurring is odd, then it is an interior contour, and if it is even, then it is an exterior contour. Let us try to find out the exterior and interior contours. Contour number 2 is having -1 only once, that means it is a interior contour. Then contour number 3 is having -1 twice, that means it is going to be exterior contour. Then 4 is having -1 3 times, means it is interior contour. 5 is also having -1 3 times, it is also interior contour. 6 is having -1 4 times, that means it is an exterior contour. 7 is also having -1 twice, that means it is an exterior contour. 8 is a separated contour, while 9 is having -1 only once, that means it is an interior contour. So the circled contour here on the slide are the interior contours, while the uncircled contours here are the exterior contours. Number 1 is an exterior contour, that means there will be some material here. Also, as 2 is the interior contour, there will be no material. 4 is also a hole, basically doesn't have any material here. 5 is also not having any material, and 9 is also not having any material. So this way you can organize the structures appropriately through a relationship matrix. So like I said, you can see in this diagram we have highlighted the region where the material is and where there is no material. Now let us assume that there is a virtual exterior contour that is numbered as 0 and it contains everything. It's like a universal contour. Now based on this we can make a relationship tree. This relationship tree shows at top, that means level 1, contour 0, that is containing everything, and then we are dividing different levels based on the -1 occurring on the row. So we have seen that for contour 1 and 8 the minus 1 is not occurring at all. That means this is level 2. Then for contour 2 and 9, minus 1 is occurring at once. They are at level 3. Also then 3 and 7 are containing minus 1 twice. They are, that means, at level 4. And the contour 4 and 5 having minus 1 thrice. And in the end, level 6 is contour number 6, which is having 4 times minus 1. And hence you can build the father-son relationship here, that 1 is containing 2, 2 is containing 3 and 7, 3 is containing 4 and 5 is containing 6. Now from this data structure we can easily observe that all the contours at the even level are the exterior contours, while all the contours at the odd level are the interior contours. You can verify also your answer here. Once we have identified that these contours are going to be exterior or interior contours, how do we assign these properties to the contour itself? For this, we usually prefer to short the edges of the exterior contour in counterclockwise manner and edges of the internal contour in clockwise manner. So, I mean to say, if number 1 contour is external contour, its edges will be shorted in counterclockwise manner. Counterclockwise manner means they will be like this. We have already seen how to short these edges. You need to just make sure that the edges starts from any point and then they goes into the counterclockwise manner. And if it is an internal contour like contour number 2, it should be in clockwise manner, means the edges of the internal contour should be in such a way that they form a polygon with clockwise manner. In a similar fashion, we can see the 3 should be like this counterclockwise, 4 should be clockwise, then 5 should be clockwise and 6 should be anti-clockwise. Again 7 should be anti-clockwise and 8 should be anti-clockwise, 9 should be clockwise. Once we defined all the contours in this manner, our data structure is ready, and now it becomes very easy to manipulate these contours further. I will show you another benefit of organizing these contours in this manner other than just identifying the region. Now, if it is required that we want to give some machining allowances to the component, then we know that the exterior contours should offset it outward and the interior contours should be offsetted inward. Then only we will be able to give the appropriate allowances. So all the exterior contours should offset like this, interior contours like this, and interior contour like this. Let us consider one more example quickly to see whether this data structure works fine for any cases. In this case now, again I have 9 contours and we have made a relationship matrix with 9 by 9 cells. Hence now we can start with contour number 1, which is the exterior contour obviously, and contour number 1 will have with 1 as relation 2. 1 is containing the contour number 2, hence 1. 1 is containing contour number 3, hence 1. 1 is containing contour number 4, 5 and 6 as well, while the contour number 7, 8 and 9 are separated. Again contour number 2 is contained by contour number 1 and it is going to have the same as 2 with 2 is going to have the 2 here because I equals to j, and also 2 is containing 3, 4 and 5 while it is separated from 6, 7, 8 and 9. Again contour number 3 is contained by contour number 1, it is also contained by contour number 2, and it is contain number 4, contour number 4, 5 and separated from 6, 7, 8 and 9. Again, contour number 4 is contained by contour number 1, contour number 2, contour number 3 and here it will be 2 and it is containing contour number 5 and separated from 6, 7, 8 and 9. Now, contour number 5 is contained by 1, 2, 3, 4 and here it is 2 and separated from 6, 7, 8 and 9. Then contour number 6 is contained by contour number 1 while it is separated from 2, 3, 4, 5. Here it is 2 and it is also separated from 7, 8 and 9. Then contour number 7, it is separated from 1, 2, 3, 4, 5, 6 and it is containing contour number 8. That means 1 here. Also it is separated from contour number 9. Then contour number 8 is separated from 1, 2, 3, 4, 5, 6 and it is inside contour number 7, hence minus 1 here and for this value 8 and 8 I equals to j, I'll write 2 and finally it is separated from contour number 9. Then contour number 9 is separated from all the contours. It is not having any other contour or not contained by any other contour. Now we can observe and I am going to highlight the exterior contours in yellow color. Obviously contour number 1, contour number 7 and contour number 9 doesn't have any minus 1. That means they are going to be definitely the exterior contours. And then the contour number 3 is having minus 1 twice, that means even value, hence it is exterior contour. Contour number 4, contour number 5 is also having 4 times minus 1, that is also an even value, hence these are the exterior contours 1, 3, 5, 7 and 8. Now I shall highlight the interior contour in red color. Number 2 is having minus 1 only once, and it is an interior contour, and 4 is also an interior contour, 6 is also an interior contour and 8 is also an interior contour. Now appropriately we can fill the material in the slice, like there will be material here as 1 is the exterior contour. So wherever 1 is going, material will be there. Then 3 is the exterior contour, hence the material will be here. Then 5 is the exterior contour, hence material will be there. And then 7 is the exterior contour, hence material will be there. And 9th is the exterior contour, hence material will be here as well. While there will be no material for contour number 2, 4, 6 and 8. Now, like I said earlier, now you can define the edges of the exterior contours in the counterclockwise manner, and you can short the edges of the interior contour in clockwise manner. So with this we completed the methodology of slicing, the different algorithms required to slice the very complicated objects also now will be easy for you if you will follow the rules which I have explained. Now let us have a look at the slicing method, which is nowadays very popular and called as adaptive slicing. So far our discussion was for uniform slicing. The adaptive slicing is particularly used for 3 major purposes. There could be some other purposes also, but these are the most popular ones. First is the adaptive slicing is used to preserve the peak features. Also, the adaptive slicing is preferred to reduce the cusp heights. And also, sometimes adaptive slicing is nowadays used to eliminate the support structures. The example of preserving the peak feature through adaptive slicing is shown here. As you can see, these are the peak features. And if I follow the uniform slicing, it may not happen that the uniform slicing is multiple of the height I am obtaining here up to the peak feature. In that case, it may happen I will end up with my layer either before or after this feature. If it ends after this feature, then it is fine, but if it is ending before the feature, then I will not have any material in this region. In a similar fashion, you can see at the other regions as well. Therefore, we have to adjust the layer height in such a way that we should be able to sustain the features. Now, you look at the same object when it is realized by the adaptive slicing. Here now in this case, the layer height you can observe is changing. As the layer height is changing, we are able to achieve or attract or capture the peak features appropriately in the part created by additive manufacturing. Also, if we use adaptive slicing, we can create more accurate parts like you are seeing here. Obviously, we know that the part will be close to the actual shape if the layer thickness will be less. But we have to compromise in that case on the time to build the part. Therefore, if we wisely choose the height of the layer in such a way that when there is no overhanging feature or there is no slant feature, we use the layer height high, and when the slant features are there, we use the layer height appropriately. Like in this object, up to this region, there is no slant feature. That means I can realize this region with the constant layer thickness, which is maximum possible layer thickness with the additive manufacturing process. But when there is a curved feature here, to realize the object in this zone, the layer height is reduced. As the layer height is reduced, of course, the region will be accurately capture the details. If I do, for example, the layer thickness here is T1 and here layer thickness is T2, and we are saying T2 is greater than T1. If we build the entire object by T1, then also we will get the same accuracy on build part, but we have to compromise in that case with the time to build the part. Therefore, if we use adaptive slicing, we will be able to save lot of time while we will be able to capture the details of the object appropriately. Also, the adaptive slicing can eliminate the need for support structures. Let us consider an example for this. If I want to build this particular part, and this is my build direction. Assume that my layer thickness is this much. This is my layer thickness, and I am building this part in a uniform layer manner. So, these are my uniform layer thickness. What will happen for a particular layer thickness? I will be getting for this slant feature a certain amount of overhang. This is called as D. Now, here also this will be same. Now, it may happen that the additive manufacturing process which we are using may not support this much overhang. It can be reduced if we use lesser layer thickness in this region. Assume that now if I am creating the same part with adaptive layers, now I can create this part up to this height with this thickness, that is maybe T1. Then this zone is also not having any overhang. I am calling this layer thickness T3. While in this zone where there is a overhanging feature and the additive manufacturing process can sustain a certain amount, maybe D1 amount of overhang, and that is very small, only this much. Then let me project these lines here and you will be able to see Now this will be my layer thickness in this zone. Hence, now you can see we are able to eliminate the support structure just by changing the layer thickness appropriately in some zones. Now let us consider an example of realizing the circular overhanging feature with adaptive slicing, and we shall try to find out the change in or the layer thickness at a particular height. As it says, the figure shows adaptive slicing of a semicircular duct. So this is the region where material is in this region. The maximum overhang permitted by an additive manufacturing process is D, that is here, maximum possible overhang. Okay, means if this is the pre-built layer, the maximum it can overhang could be D. This is the value D. It is asked to determine the following. First, find the expression for nth layer thickness and find the minimum layer thickness in the process. It is obvious, as this is the boundary which I am going to realize. To keep the overhanging feature constant, because I can't go beyond this value, the layer thickness will keep on changing. You can easily do that. Just draw the overhang here and correspondingly protrude it upward, here also and here also. So it can be observed that the layer thickness will change. Here it is T1, here it is T2 and so on. So let us consider the profile which is having the inner radius R. Looks like this. This is the inner radius. So distance from here to here is nothing but R. Now if there are certain amount of layers here, I am considering a node at this point, and this node is at a distance ND from the left, from here. As it is the nth layer, it is forming the nth layer, this particular node will be having ND value, because each layer is having D amount of projection on the x-axis. This is the x-axis. Hence, n layer will be having ND. It is obvious. As this is ND, of course, its bottom slice will be intersecting with this curve at n minus 1D. And as this distance is R, the distance from here to here will be R minus dn. Now we can easily write down the coordinates of this point and this point. The x coordinate of the nth node of this node will be nothing but minus R minus dn, because this distance, and this is 0 comma 0. I can go in this direction minus. Hence minus R minus dn. Now the y coordinate of this particular node, this nth node, will be equals to under root R square minus R minus dn whole square. How we have obtained it? We have obtained it by the equation of the circle, because we know that this is a circle which is having equation x square plus y square equals to R square, because its center is at 0 comma 0. And we already know the xn, we just replaced xn here, and we can obtain as a result yn, and that is why we did. Now the thickness of nth layer will be nothing but, if this is yn, the thickness will be nothing but yn minus 1, the y coordinate of n minus 1th node. Hence Tn will be equals to yn minus 1. Now we can easily find out yn minus 1 also, just by replacing n by n minus 1, and hence your Tn will be equals to square root of R square minus R minus dn whole square minus square root of R square minus R minus d and minus 1 whole square. So this expression is giving us the thickness of nth layer. Now if we want to find out the minimum layer thickness, we know that the minimum layer thickness will be obtained at the top of this circle. It is because the slope is 0 here, right? And hence the minimum layer thickness will be obtained at this particular layer. For that, of course, we need to just replace this distance when the node n is not here but here. It is obvious, in that case nd will be equals to r, means I am considering now from here to here the entire distance. So let us replace nd by r, or in other words n equals to r by d, and let us replace n r by d in this equation. You will be able to find out the minimum layer thickness as T minimum equals to r 1 minus root over 1 minus d by r square. Now let us assume that you have an additive manufacturing process in which the minimum layer thickness possible is 0.1 mm and the material which you are using allows a maximum overhang of 1 mm. In that case, now what radius I can build through this process for a duct? The internal radius. So we know that T minimum is given to us, it is 0.1, and also D is given to us, it is 1 mm, and hence I can easily find out the R will be equals to 5.05 mm. That is the minimum possible radius of the duct which can be realized through this process. Thank you very much.